Recording started.
Okay, great. Well, good evening, everybody, and thanks for joining us. I'm Dave Bartle. I'm the local rep for the Institution of Civil Engineers in the Calgary area. So tonight's presentation is, you can see, seamless chemically post-tension concrete slabs systems by Alphacon design. Shrinkage-suppressed chemically post-tension flat work. So we've got two presenters this evening. We've got Francois-Xavier Destre and Professor Dr. Kevin McDonald. Francois, as some of you may have heard, he's actually based out of North Carolina, but he is in Calgary right now. He has been involved in many industrial shrinkage-suppressed concrete slabs in this area. And I was going to confirm that he is in Calgary. I did see him yesterday at one of my recent projects. Dr. Kevin McDonald, he is located in Wisconsin and Minnesota. He's a professional engineer registered in Minnesota, Ontario, and Alberta. He is also president of Beaton Consulting Engineers, and their specialty is concrete. So I will hand over to Francois.
Well, thank you very much, David, to host us and to be our sponsor and champion tonight. It's a real pleasure for both Kevin and myself to have such a good audience. And today, the primary objective is going to be to educate, to address questions, and to also present a technology which our audience may not be accustomed to. So indeed, this is about the future of concrete building, and the future of concrete building must address common and historic issues with concrete. And these two issues include shrinkage, as well as the production of CO2 upon using and producing cement. So with this presentation, I will first allow everybody to meet their trainers. With that, I hope I can go to the next slide. If I am able to. Yeah, that's not right. Next one. Let's see. Okay, so I'm going to talk very little amount of time about myself. But my experience and track records is mainly with engineered slab systems, which are engineered in a way to not have joints, to have minimal shrinkage, and to use steel fiber reinforced concrete, thus steel fiber reinforcement as the main avenue of reinforcement. That is, thus not using conventional shear reinforcement such as rebar. The objective with this is to provide an homogeneous reinforcement and to design concrete bodies based on their real needs, that is based on a certain loading program. So this is really anchored in reality with real projects. And as far as I am concerned, I have been able to help design and build in an engineering lead and owner quality large concrete systems, including for the highest automated warehouse in the US. That's in Tacoma, Washington. You'll see that there in 2016. There is a lot of track record as well in Calgary, including the largest pile suspended, so suspended slab or pile supported, that is without ground support, and designed and built without any conventional shear reinforcement or rebar steel. And it is indeed with a very high dosage of steel fibers by controlling shrinkage. That's in Calgary. And that references a very large Home Depot distribution center. There's much more, and I don't want to discuss that too much, but many of these can be visited. And currently my track record for those turnkey design build and joint-free concrete bodies exceeds 75 projects. Now, I would like to introduce my co-presenter. So please meet Dr. Kevin McDonald, who, David, thank you for introducing both of us. I believe you mentioned that Kevin has engineering credentials in both the US and Canada. And Kevin also serves as an assistant professor at the University of Wisconsin, construction indeed, and serves as a chairman for ACI 302, and ACI 302 is concerned with slabs on grade. So certainly a very skilled engineer with a specialty indeed in mechanical, structural engineering, and also forensic engineering. I know that Kevin also is very skilled in petrography and runs a petrography lab in the US. You can see Kevin has many awards and achievements. Kevin will gladly present the design aspects of this presentation, and we try to make that design portion of this presentation very real, and that is to tie it to real projects here in BC and Alberta. So we will discuss some considerations that are indeed fundamental and at the crux of concrete design. But first, what are we really going to discuss today? What type of projects? Well, when you talk about high performance concrete systems, and in particular flat work, you're going to talk about industrial concrete because it comes with certain performance criteria which might be different than just residential commercial applications. We're talking about point loads, we're talking about heavy traffic, we're talking about complex racking. So with that, you are going to look at flat work, essentially slabs on grade, slabs on insulation, and that's for specialty food distribution. Third-party logisticians today are building a massive amount of extra food storage, and you're talking there about coolers, freezers, indeed. Some of these DCs or distribution centers can be then automated. In that case, they're provided with cranes with very little labor, and these cranes, because of their operation, calls for everything to be automated. Now, these facilities are then also very high rise, and that's not without certain structural constraints if you are designing a structural foundation system which holds everything together, considering you have a very high rise building. But we can introduce already the future, because the future is already happening in Europe, and it will soon here in Canada and the US. But what we'll discuss today can also be applied to foundation systems for residential condo towers, including, as it is done widely in Europe these days, with those built close or close to and even underneath the sea level. So what we'll discuss today, with very few modifications, can be used for elevated suspended structural floor slabs. You find those in every high-rise residential building, condo towers indeed. And it can also be used for infrastructure projects where you have certain performance demands which can be addressed by indeed suppressing concrete shrinkage and designing concrete optimally. So how do we do that? Is really the topic of this conversation today. So the topics, indeed, certain historical facts in concrete R&D, slab systems. We'll look at how what we do work. Then we'll talk about the design practice, which will be the chapter of Kevin more specifically. We'll look at certain system install considerations, and then we'll try to understand what are the long-term benefits for shrinkage-suppressed concrete. And some of them are obvious, some are a little bit less obvious. So starting with the history and overview of concrete, we have to ask ourselves, why do we do this? Well, it's very simple. Concrete is the most widely used composite material in the world. And yet, it is still very difficult to find thin, light, and durable concrete, just as you would find at the crux of the design of any composite. And these composites, they are everywhere in our daily life. And it seems that concrete, on the other hand, hasn't gone through the improvement curve that has been observed for other composites. So the idea here is to design much better concrete that is performing much better. And that's certainly not by having the maximum carbon dioxide footprint for that concrete body. That is not by having maximal drying shrinkage, which is the mother of all problems in concrete, drying shrinkage. This is not by having continued and costly inefficiencies for owners to deal with, or their tenants, or the users. And this is not to have durability and performance issues. Well, you might tell both your trainers today, Kevin and myself, that that's impossible what you are proposing. Well, it is possible. And it is possible. It's important to realize that concrete production today is 8% of the total of global CO2 emissions. That's a fact. Better concrete bodies will use less cement by being thinner. That doesn't mean they are not going to perform as well or much better. And that is indeed at the heart of our message today. So why don't we have today everywhere fantastic concrete that performs well, that doesn't have shrinkage? Well, because this is all something that has been forgotten. In fact, Romans were designing concrete, and if you have been to Italy, you've seen concrete that performs very well, and that is without shrinkage, without cracks. And the only fear for these concrete monuments might be birds who appreciate standing on those monuments. That is the only problem, but that's more corrosion related than anything. So let's look a little bit at how what we are doing was made possible. But first, in the early 80s, my father, Xavier Destre, a Belgian engineer and peer of us here, indeed put out the first patents. His objective was to design joint-free steel fiber reinforced concrete, and with steel fiber indeed in an adapted concrete mix would then control shrinkage, would not suppress it, but would control shrinkage and prevent the proliferation of sewn joints or essentially induced cracks in concrete, which is the only solution found by mankind before that to really suppress joints other than cable post-tensioning or other avenues to reduce shrinkage. But fundamentally, that first patent laid out a path for maximal performance steel fiber reinforced concrete, indeed, with all the design practice, the type of fiber you want to use, the type of mixes that are going to work well with that steel fiber. So the manifestations of drying shrinkage, even with high dosages of steel fibers, were still showing. And in other words, that's because when you control shrinkage in concrete, you redistribute cracking in concrete, but shrinkage is still there. So the path did not come to an end until my father and his partner, Johansen at PrimX, decided to study Roman concrete. And to do that, they collaborated with 5 universities in Europe. They obtained a European Commission science funding, and they went on to look at Roman concrete like never before. But there was an objective behind that technological breakthrough that was to truly suppress drying shrinkage. And doing that was a real challenge. But with everything done in that research program, the first distribution center using this PrimX technology that we are going to discuss today was built in Sweden in 2007. And so you can see this is no longer new at all. So in North America, the presence starts in 2011, 2012. There's a lot of patents protecting indeed the intellectual property and the discoveries of what has been that will be presented today. But what we're presenting today is really a way to advance better concrete that is performing at a higher level, that is extremely durable and more durable than ever before, and also socially responsible by also causing for less cement to be used. So the presence of this technology is very widespread, as you can see. There's over 200 million square foot installed and growing. That is just for flat work. Okay, there are other concrete bodies than flat work indeed, as we discussed. And these bodies are not counted in terms, of course, of square feet. But when it comes to concrete flat work, and that's industrial slabs, essentially, 200 million square foot are installed, that is designed and built, and this is growing very fast. So how does it work? Well, PrimX concrete works, and I'm going to explain this extremely easily in an easy fashion. Kevin and I will take questions at the end, so please note your questions. We're going to try to make this very simple because we believe that something simple is, in fact, able to perform better. Every engineer wants everything simple, continuous, linear, and homogeneous, and this is no different. And that's probably why it works. So you have to use high tensile strength steel fibers mixed homogeneously in concrete. These steel fibers, they make up for reinforcement, but then you are going to provide that concrete with a shrinkage suppressing additive. It is a cementitious additive that is causing for the concrete to book a net expansion over very long times. In other words, you are securing the absence of shrinkage, of drying shrinkage, by instead causing for that concrete to expand, except that now that concrete is provided with a great amount of high tensile strength steel fibers. Tensile strength of the steel is about 1200 MPa. This is 3.5 times what you will get in usual rebar steel, by the way. And when that concrete is set, a couple of days, day or two after it has completely set, that nothing can move, it's not plastic anymore, it has set, it expands, except that concrete is now very heavily internally restrained. Now, you have now an expanding concrete body that is internally restrained. That is going to cause for that concrete body to be self-stressing. In other words, to accommodate pre-stressing, to essentially, from the start, be pre-compressed. Okay, so that's why we call this chemical post-tensioning. It is a form of post-tensioning, except you are not using steel cables, if you're familiar with cable post-tensioning indeed. That is not enough. You have to have a quality management process to ensure that this works every time. And that quality management process is central to every step, that is from the design to the selection and due diligence on materials, laboratory tests, in order, for example, to quantify nominal shrinkage so that you can better fight it and suppress it in order to indeed secure a net expansion of your concrete body at very long time. So these three elements, that is a quality management process, the data gathering associated, the due diligence associated, including on concrete materials at every and each project, that creates the PrimX shrinkage suppressed concrete bodies. So very quickly here, the science behind the system. Well, when you have a conventional slab, and I think this is going to be good for all the mechanical engineers, because this is really concreting or mechanical engineering applied to concrete 101. But if you have a conventional slab, from the moment that that slab has shrunk, well, it has experienced shrinkage tensile stresses, and these tensile stresses, they superimpose themselves to any load or mechanical reaction that you are going to put on that slab. And as a result, that is causing for your slab to have a more significant section of it in traction. Well, we don't want to design concrete in traction. It's always better to design it in compression, where it is 10 times stronger indeed. And so there is always an interest at trying for that neutral axis within your section to be as low as possible, because if you do that, well, then that concrete body works in compression, okay? So if you take a mechanical effort that is causing for that axis to be as we see there, and you add the tensile stresses, but you also add some pre-compression or self-stressing, as we discussed before, then your concrete section can actually operate in compression. In other words, you have improved the baseline design of your concrete. Okay, so you can see if you are using self-pressing, then that concrete is going to show, that section is going to show a neural axis that is going to move lower down in that section. Okay, so what does that do? Well, concrete that works in compression is concrete that is working for you. In traction, it's not. So what about using concrete that is actually working for you for a change? You might be able to put concrete at work and use a little bit less of it by making it work better. Okay, so that's in a very qualitative explanation. We can go more into the details indeed if required here later. Okay, so you can go joint free with many methods, huh? If you want to address shrinkage. Some people use macro or microsynthetic fibers that control shrinkage a little bit. The reality is macro and microsynthetic fibers often don't even modify your stress strain curve, so that your ductility improvement is almost, I wouldn't say insignificant, but very insignificant when opposed to other reinforcing avenues such as steel, including rebar and steel fibers. But that's what you're seeing there in blue. You see there is not a lot that can be offered by that avenue. You can use normally steel fiber reinforced floor. You can increase joint spacing with those. Problem is, you're not going to check on everything here from the moment that you still have drying shrinkage. And you can use good old type K shrimp concrete as well. That is a technology that was invented in 1953 by Dr. Klein, hence the type K shrink denomination. But that's a one-size-fits-all approach. And that does not yield as much as positive and usable features than what we're using, which is no shrink, no sockets, as you see there in red. And traditional concrete has everything wrong, simply because it will shrink extensively. And with that come all the problems that you don't want to see in a concrete body. That's cracking, that is large joint openings, dominant joints, sockets, curling, often with very undesirable outcomes and costly outcomes. If you are using forklifts or engaging in heavy-duty operations such as distribution, manufacturing, and other activities alike. Okay, so I'm not going to go into the whole thing. I think you were able to look at this, and we can address more later. On the design practice, I'm going to, Kevin, you were introduced. I think it's your turn. Just let me know when you want me to pass the slide.
Terrific. Well, and thank you, Francois. I think you covered some of those slides very well in terms of the stress distribution within a slab member that's shrinkage compensated. If we look at typically we're looking at slabs on ground. We can look at those loads in the Canadian in the CSA code. They are, unless you're passing other building loads into the slab and thereby into the foundation, it's independent of the design is independent of the rest of the structure. And we've got lots of interesting load conditions that occur on slabs on grade. We've got rolling vehicles. We'll have very large static loads. We have moving static load or alternating static loads that change. And of course, we have the condition where the slab is, if the slab is continuous, that we can get a positive moments occurring in the aisleways and negative moments occurring beneath the racking. And so we get quite a bit of problems. And one of the ways that we control that is that we've been traditionally cutting joints into the slab. A traditional method, and one of the methods favored by designers here in the United States, is to have a low strength, and by definition they infer that means low shrinkage concrete mixture on a relatively flexible subgrade. So, 0.05 kilonewtons per meter. Although I grew up in Canada in slabs, I think in imperial and heat transfer, I think in metric, but so if I've got the wrong units there, my apologies. But we look at the slab, and that slab distributes those loads down onto what's below the slab. We've done a number of freezers with Francois, where what's below the slab is a styrofoam extruded polystyrene insulation that has certain properties in terms of how it's going to respond to stress and how it's going to deflect. And we use a whole bunch of methods of analysis to look and see where we are. Both a finite element analysis. You can also make some simple finite difference models, and further, we take into account the unique properties of shrinkage compensated steel fiber reinforced concrete. So those of you who are familiar with reinforced concrete design probably remember we solved a lot of our problems in the 20s by using the Whitney stress block, assuming such things as not only does the concrete have a tensile strength that's order of magnitude or so smaller than the concrete in compression, we go one step further and just say it doesn't have any strength and tension. And that's a very safe assumption for us to make. We go on from there and say at that point, we're going to make the steel yield and we make structures safe. We get some cracking in the at the bottom in the negative moment and at the top at positive moment locations of a beam, and the slab really is just a beam on an elastic foundation. That that's how we're going to handle it. And we have to resist the stresses that occur due to curling. And those stresses are because the shrinkage in a slab on grade are not uniform, or slab on insulation or wherever else. They're not uniform. They're going to be more shrinkage stress at the top, less at the bottom. So from a shrinkage compensating concrete point of view, the concrete will still shrink. We know that the Portland cement is going to shrink. It's a normal activity. What we do is we design the slab so that it expands a sufficient amount so that at the 10-year or 20-year shrinkage, there's a net compressive strain throughout the thickness of the concrete. As a result, you get no curling, no warping of the slab, and therefore no internal stresses that are already built into the system prior to loading with forklifts and racks and storage and all sorts of other things. The great advantage of doing that is that about a third of the capacity of the slab is used up in dealing with those shrinkage stresses. If you don't have the shrinkage stresses, you can make the slab thinner, use less material, and still have the same resistance to bending and cracking. And an operating definition for engineers is a person who can do well for $1 what any fool could do for $2. So if you use less material, you're spending less money, which is a desirable outcome. We get what we need and we use fewer resources. But in addition, we reduce significantly the emissions that are associated with manufacturing that slab. That's a double good thing. Klein and all that type of work that was done in the US in the 60s involved individual reinforcing steel bars. Put it in at a certain reinforcement ratio, you place it in a slab in the upper third of the slab, because frictional restraint at the bottom will give you some additional restraint, and they built lots of successful structures that way. The difficulty is that the capacity of the slab is still determined by the cracking stress and the cracking moment, associated cracking moment. And so instead, what we can do in our particular case is, with the presence of steel fibers, we can make a lot of assumptions about the performance of the slab that do not require us to worry about a single crack developing, as will happen in a brittle ceramic like concrete. If we instead consider what happens. We have a plastic hinge, much the same as we would if we were designing a piece of steel. And so, you know, those of us that have been around for a little while remember when we did not use plasticity in steel. We used working stresses, and we kept below the yield strength. And we know that our ultimate limit state can be set to being some plastic deformation, and we increase the capacity and the performance of the same amount of material. Doesn't really work very well for concrete unless it's steel reinforced, and it doesn't work extremely well for slabs on grade, because you then have to have 2 mats of reinforcing steel everywhere, and that becomes a construction problem. The construction labor problem is as big in the United States as it is in Canada in finding experienced labor. And you end up with people who know that the easiest way to build a slab on grade, if it has steel reinforcement in it, is to kick all the chairs off and push the steel to the bottom. It's also a safety issue. You have to step around steel that you can't see while you're placing it. So putting steel fibers in gives us a constructability advantage. These fibers are uniformly distributed. That's where that quality management program comes in, to ensure that that's the case. But we treat the slab, and the illustration on the screen shows a slab that's being loaded. We're going to get positive moment cracking that is radial from the load, and we'll get negative moment cracking circumferentially. The plastic hinge, as some of you know, is a work method. It's the amount of work done by the load has to be balanced by the amount of work that's done by the slab. And so we can run these analyses and calculations and find, in fact, that we can get a resisting moment or required resisting moment from that type of analysis. And that resisting moment is much higher in steel fiber reinforced concrete than it is in conventional unreinforced or mildly reinforced against for crack control slab reinforcement. Where this really gets interesting is that as we increase the steel fiber dosage, the size of the crack, the mean width of the crack, decreases significantly. And so instead of having a single crack as we would in a plain concrete, or discretely balanced cracks the way we would see with discrete reinforcement, we get hundreds of cracks occurring in a short distance. But the cracks are very, very narrow. And as we all go through our infrastructure construction, and we've been involved, among other things, in the light rail construction in Edmonton, looking at the durability of these concretes, they are more resistant to fluid penetration with and without chlorides than conventional concrete is in any way you choose to measure it. So we can have the next slide. And probably there we go. So when we use a finite difference analysis, we can come up with what our moment distribution within the slab is. We make some assumptions. We have a constant modulus of subgrade reaction. We have some free ends, this constant cross section, and we assume that we're on a Winkler subgrade, that the pressure or the bearing pressure is linearly proportional to the deflection and is only occurring in a single direction, in the up and down direction, and the applied load to the center of the beam. If we do that, we'll have the next slide. And there we go. So if we look at a beam on an elastic foundation, and this is a calculation based on some point loads, you can see where the bending moments are causing the slab to bend. That's perfect. Leave it on that one. And we look at the shear as well. The nice thing about the steel fibers is that they work both in shear and in flexure. And we come up with our loads. Apologize for the archaic units, but and I do live in an archaic country. I'm a Canadian citizen, by the way. I grew up in a city a little bit east of Calgary. It's probably not worth mentioning what its name is. And if we look at that, if we can go back to that slide that shows the finite element analysis, so that's we can also look at a finite element analysis to get us stresses. Now, if we go and make assumptions now about the moment capacity of the concrete, and using our failure as a first crack in the concrete, we will get a very conventional slab. If we take all these analyses and then apply a yield line resistance concept, we can find a great additional capacity. Yield line analysis gives us a more appropriate determination of the actual stress distribution and moment resistance that is present in the slab. We have an issue as engineers in that you know, we pardon the pun because I teach at the University of Wisconsin Stout, is that when in doubt, make it stout, right? So when we're not sure what the loads are, we'll just make the member bigger. Then we know we feel a little bit safer, and of course that violates my earlier rule of doing things with as little resources as possible. Sometimes it's interesting to see that you have a structure that is built using a modern analysis, but the slab on grade is being designed using the American Concrete Institute's methods, which most of which are based on working stress. And if you apply modern analysis, as we're talking here, you get a very different result. And of course, there's nothing wrong with a safety factor of 5 or 6, except that it's someone else's money. We'll have the next slide. And one more.
I think we're going to shift, Kevin, to the applications. Huh? So the first one being the BC application, I believe.
Right. So that's the theory, and Francois laid out the stress distribution and why shrinkage compensation works. And it's one thing to talk about things theoretically. It's something else to go into execution. And so we thought we should talk about we have a freezer that we designed the slab for in Burnaby, BC. 64 kilonewton loads on a 6 millimeter thick 200 by 200 millimeter base plate, 32 kilonewton per wheel moving load, and a uniformly distributed load at 50 kilonewtons per square meter. These loads are relatively high. And of course, the issue we have in British Columbia, as you do in some parts in Alberta, certainly in the Northwest Territory, is some seismic issues. So we perform the analysis. We don't use ACI 360 in this particular case. We used a publication of the Concrete Society in the UK, TR34, which is a much more advanced document. In that design, we came up with a slab thickness at 100 millimeters of shrinkage compensating steel fiber reinforced concrete with 40 kilograms per cubic meter of fibers. The joint spacing is infinite. It you can place shrinkage compensating concrete continuously and never have a joint. People get tired doing it, but it can be done. But you only need what the Romans used to call an end of day joint. You only need to end the slab at a particular location and pick up the next day. And if you've designed things properly, then you don't have a problem. The foundation immediately consists of 100 millimeters of extruded polystyrene insulation. So we don't have a very stiff subgrade, even if we have the soil below the insulation compacted to a relatively high stiffness. The insulation stiffness is limited, and when they talk about the compressive strength, in this case, it's not very high. Maybe I think it might be 275 kilopascals. It's not, that doesn't mean that's the compressive strength as the way you would look at a concrete or steel. That's the force or the stress that's required to punch in a disc to a depth of 1 inch. So you really have to be careful with the insulation as to what its loads are. have the next slide. As I said, the structure is interesting in that it's in a very high seismic area, and so we wanted to check based on the geotechnical engineers' recommendations how well the structure would do if we had the worst condition, which is a top rack that is at its full load and nothing on the racks below. So we calculate the punching shear and the bending forces that would occur during that seismic event. It's just a post load of 135 kilonewtons. This gives us a punching shear at 0.54. And it should also be in force and not stress. The capacity of the slab is about 6 times what is required. And so we were able to determine that the slab had capacity to resist its shearing, punching under the seismic loads that were anticipated. The structure would likely crack because we have it designed at the 64 kilonewtons, so the structure won't crack in service loads. If we more than double that load, we would crack the structure, but a cracked structure that is still standing is a victory in a seismic event. So we'll have the next slide.
Yes, I wanted to add to this, Kevin, that the Burnaby freezer is showing a monolithic slab which extends 26,000 square feet. And because of the owner's requirement, that footprint for that slab looks like a piece of a puzzle with many re-entering corners, which we all know are consistent with crack initiation. For instance, in this case, all these corners are treated with certain details, but the message is you have now an owner that can operate 26,000 square feet. That's a little bit more than 2,400 square meters without one single seam, joint, and as a matter of fact, in Burnaby, without cracks. Now, concrete cracks, but we never sell crack-free or promise crack-free, but we look at lowering the probability of cracking drastically so. And so in that way, that concrete body is exceptional by the fact that it is 26,000 square foot, absolutely monolithic, to the great joy and pleasure of that donor, which really is achieving exceptional outcomes, and especially when considering that slab is 100 millimeters thick and was designed with full shrink concrete and bars at 9-inch before we came in to offer that owner a beautiful, extremely durable, seamless, and monolithic body. And I'm going to go ahead to the next slide, which talks, Kevin, about another type of project.
Yeah, so there's a number of structures that are rack supported. Essentially, the racks don't just hold the goods; they also form the columns that hold up the roof, deal with wind loads and that sort of thing. This particular structure for Conestoga in Calgary has 148 foot high. So what is that? about 49, 48 meters, with cranes on rails operating within the structure. The racking supports the cladding and the roof, and it's a freezer. It operates at -25°C. And the issue that came up, of course, is that if you have the wind blowing in just the wrong direction, we can have a very large uplift force, and it is foreseeable that the rack could be empty in that location, and so there's no gravity resistance from the goods that are stored. The slab thickness was inadequate for anchorage, and so we designed an internal beam that sits inside the structure and resists those uplift forces, mainly by providing additional confinement for the adhesive anchors, in addition to to providing some additional bending capacity right where it is required. If you go in a couple of column rows, the uplift forces are pretty negative, or pretty minimal rather. And so here's an idea of how at the end of those slabs, how tightly these racks are sitting. We flared it out so we had additional uplift force resistance. That was designed by the racking manufacturer, but the beam, as you can see, has basically a box beam to resist the uplift bending, and then some hairpins and close stirrups to provide additional confinement for the anchorage. Again, you can see these types of the types of loads. You have 393 kilonewtons is the design load on a single post. Very high loaded. Again, a small 200 by 200 millimeter base plate, and it is performed. It's under construction, right, Francois? That's why you're in Calgary.
I was actually there on site again today. The cladding is almost finished. Another design consideration of interest is the erection of the racking system is going to cause for a crane to reach out 200 feet high. And so those cranes are actually installed preliminarily on the slab. They can travel on rails, and they then can sometimes call for a supplemental design check. Even though the crane is not going to stay there, it has to reach out extremely high in order to be able to erect the racking, including the top members. I mean, as Kevin stated earlier, it is 148 feet high. But evidently, there's not going to be any forklift in there because it's all dark, automated, and crane operated. The slab thickness was 53.5 centimeters. 21 inch, but that was a reduction from a conventional mat slab system, which would have had 2 or even 3 rebar mats. And from I think from an operational point of view, finishing with the right very long distance levelness that is required, a very large concrete body that is fully monolithic, and finishing that concrete in the presence of those rebar mats can be strenuous, if not next to impossible. Hence, again, shifting to steel fiber reinforcement at extremely high dosage, and in this case, 40 kilo per cubic meter, helps the team. And then imagine the hundreds of anchors that are drilled in after the slab has been installed, hitting the rebar. What a nightmare if you are indeed the racking anchor installer, whereas in steel fiber reinforced concrete, you are not going to hit bars. So that's another efficiency in terms of productivity, and also an error-free install of those anchors. And Kevin, I interrupted you. Back to you.
Well, no, and those are excellent points. The biggest difference is the amount of labor cost that is involved in tying the reinforcing steel is very high. Relative to the amount of additional labor that it takes to put the steel fiber reinforcement in, which is very small, it makes a big difference. And the reason that we're able to do all of these things and reduce these slabs is because we understand the mechanics, the chemical and physical properties of the concrete that we're using, and we can use that to our advantage to make sure that we're getting what it is that we need without having to have unnecessarily high safety factors. So it's a very interesting design aspect. As here, it's much more than just a slab on grade. It includes itself as a mat foundation. So the next slide.
Yes, and I believe, Kevin, this is the tallest freezer building ever built in Canada.
That's my understanding. Yes.
So we have a detail of what we were discussing before here.
Yeah, one of the things probably to remember is that shrinkage compensating concrete requires a secondary reaction for expansion, And so we do maintain the slab in a wet condition with standing water on it for 14 days. That's not for the regular conventional reasons for curing. It's to provide water to allow that crystalline growth to do the expansion. And so you get by default a very, very dense slab. And the most important thing for these high racks, if you think about what a differential of 5 or 6 millimeters is at a height of 50 meters, is the slabs are dimensionally stable. They don't shrink and curl and move around, and that makes a huge difference. So I think that's important to see. Well, these are the loads and the dimensions that we had talked about on the last slide. So in the interest of time, we should probably go to the next one.
Yes, indeed, and that's going to be back to me. Thank you very much, Kevin. Kevin, you interrupt me if you feel you need to on the next one. One thing we didn't say, but I think it is self-explanatory to some of us, at least I'm sure, is that structural mat foundation system that that Kevin just discussed is fully monolithic and does not come with seams, joints, construction joints, expansion joints. You cannot have those. Imagine thermal retraction within that system with these cranes operating with very, very small tolerance. You can, of course, not allow for these joints. You have to, if there is thermal retraction, and there is some thermal retraction, it has to be met at the perimeter and certainly not within the monolithic concrete body. So
yeah, it meets that. It meets that engineering requirement of being better with less material.
It is, because I think that the original design was about 30 inch. In this case, we are at 21 inch. But another aspect of these concrete bodies with homogeneous reinforcement from top to bottom is that the whole section is at work. If you've got a concrete body with more than one rebar mat, well then the structural properties are given by the distance between the top and the bottom rebar mats. I mean, that distance, the square of that, indeed. So then you have a lot of concrete below the bottom bar mat and above the top that is not at work for you. Okay, so this is not the case, because in a system that we just described, the whole section of that mat slab system is at work, fully so. Kevin, would you like to comment on that before we go?
No, I think that's exactly the point, that the slab performs better than a thicker slab with additional reinforcement in it. And the fact that the steel fibers are uniformly distributed, and that's that quality management portion, gives you the performance that you want.
And so we are going to move on to the system install. How do you make that concrete? Well, first of all, there needs to be a due diligence process ahead of any kind of operation. So essentially that means sampling sand, aggregates, completely qualifying cement from the paperwork that comes from the cement plant. You're going to look at the finesse blend. You're going to look at the different mineral phases that are present in your Portland cement, which we use type 1 and type 2, but that doesn't mean that cement is everywhere the same. It doesn't have the same reactivity. It doesn't have sometimes exactly the same exothermic reactions upon hydration. So all that is actually completely qualified, including by pouring beams per ISTM to qualify and quantify shrinkage, not only in its amount, but also for the way shrinkage occurs within a timeline. Okay, there is ASTM protocols for this, and that's part of even before the placement. So now you've made your concrete mix and you've qualified everything. Well, the concrete plant is going to make a very simple mix, and what is simple performs very well. And what is a simple concrete mix? Water, cement, aggregates, sand, and that's it. So there is no messing around with additives or changing things or trying to hide anything. It's fully transparent. Then that concrete's going to come in the truck on site and will start to become improved. And it is becoming improved by blowing the fibers at very high speeds inside the truck. The truck is the worst mixer in the world. I always say this because there's no energy to mix at all, unlike your kitchen blender. But it puts the materials in that truck in movement. And that means that if you are blowing fibers at the back of the truck, every little element of volume of concrete will see incremental fiber additions over time because the truck moves those materials very well. It doesn't mix them well, but it moves them very well. So that is not enough. We have to use a cementitious additive, which is then hydrated on site in a known dosing fashion. That proprietary additive is what is going to secure in an excess water situation, just that Kevin mentioned earlier. We use 14-day wet cures on all these slab bodies, but it's going to indeed be added at the same location. You can see on that picture, there's two fiber integration machines. These fiber integration machines can also dose a rheology modifier in concrete in more working terms, super plasticizer indeed. And the fibers, and then the yellow machines, you see that what they do is mixing the cementitious additive that we have and injecting that slurry in the truck in a known and dosed fashion. What are the dosages? Typical dosages of 40 kilos per fibers. Depending on the type of cement you have, it can vary, but it's typical to use 40 kilos of cementitious additive plus the water that goes with it to hydrate it to make that slurry per cubic meter. Okay, that has a huge advantage because you're essentially adding more cream to that concrete, which makes it much nicer to finish. The message is that we, design build contractor like Alphacon, for which I'm one of the owners, is going to take indeed the responsibility from due diligence to making that mix, so we work very closely with ready mix suppliers, but they put in their mix what we tell them, and not vice versa. So that's what an installation setup is going to look. For every truck, you're going to have your additive, which is called DC. You're going to have your flow, which is the rheology modifier, Super P. You're going to have a fiber blower. And typically you are going to have two of these sets working in parallel on site to improve concrete. So now we're going to spend a little bit of time, and we're 75% down into this presentation already. Time flies. But we're going to look at the benefits if you're an owner or tenant of shrinkage-suppressed pre-stressed concrete bodies. And we are going to, just as we did before in this presentation, we are going to limit the focus of this to concrete flat work. But keep in mind that flat work may be suspended, may be elevated, okay? And that flat work doesn't have to be flat. I mean, if you're build it, there are certain concrete bodies that are not exactly flat, but they can benefit from this as well. And it is being done in other regions of the world already using this technology. But we'll keep it to concrete flat work. So now, if you're thinking about the benefits of doing something, you gotta ask yourself, and that's always what a good engagement or salesman does, is to listen to the client. What do they want? What's their experience? What do they want to get rid of? What's the problem they're experiencing? And so, yes, they all want higher productivity and safety. That's higher speeds. They want data-driven and flawless operation, no accidents, maximal safety. They want also minimal maintenance, not only to the slab, but also to whatever operates on it. And then you're talking, of course, at mechanical handling equipment or forklifts. And forklifts, they suffer tremendously from driving over sound joints or socket joints, you need control joints. In fact, their wheels are mostly, when I say mostly, it's for the most part, damaged and worn by socket joints, not by driving around a nicely finished slab, not at all. And it's a cost that is often buried, but it is a cost that is tremendous. Imagine I have a worldwide retail client who did a test here in Calgary. And in 2011, they were spending in a freezer $31,000 US per 100,000 square foot per year on wheels. So if you have a 500,000 square foot facility just on wheels, because of your socket, you're already spending 160,000 US dollars of 2011. Okay. So a lot of people don't even realize that. And we haven't even spoken about product loss, safety problems. What's the morale in a facility, in a warehouse where the slab doesn't even look good and everybody works on it every day. You know, so some matters are not exactly quantifiable, but these matters are very real, and they can undermine the bottom line of any user or any tenant, especially a smart and mature tenant who knows where their money is going to. So another thing that has happened is an increased focus on facility hygiene. It is very, very clear that if you're storing food in a freezer that is full of debris, germs, broken wood, previously destroyed product that wasn't exactly cleaned up, go ahead and clean something in a freezer. It's very, very, very difficult. So if you have a bad slab, that product loss, you can get rid of it. It goes into sewn joints. It's really the perfect storm if you are a freezer owner, because repairing in freezer conditions is very hard, but it is actually the perfect storm even if you're operating at ambient temperature for the reasons I stated above. And then, you know, in the recent years, we've seen that the CO2 problem became more a societal problem, and the social responsibility with this and building leadership is also an enormous factor. And it is very clear that if you can suppress cement or cut down on cement use and have a much better product where you don't have to caulk joints and use more material over the years and come back and repair, and you can also in the first place lower that CO2 footprint, you're going to have a very good way to talk about benefits. And all what's on that slide says what the owners want. In other words, they also want a slab that is very durable, for which the workability stays the same. And that means for that slab to stay flat, and that means for that slab to not curl. Well, guess what? Every socket, every control joint curls, even though minimally or maximally they will curl. This is very bad, and that tells you also that if you are measuring flatness and levelness, in particular flatness on any slab, you can come back 10 years later and you don't have the same report. Absolutely not. That report is going to tell you how the slab performs 24 hours after it was installed, and means nothing to anybody operating that slab 5 years from now. Why? Because that slab is mediocrely designed and designed to continue to demonstrate and show all the effects of shrinkage, which we are proposing to suppress. So we're looking at concrete bodies on the long term here, and with recurring very significant benefits and savings for an owner. You can read this slide. I mean, cleanness, flexibility, social responsibility. That's another way to nicely put what we just discussed earlier. So if you look at the numbers now on CO2 reduction, I would like to point that out, as well as on the mechanical aspects of things. But look at the base design of, let's say, the 9-inch fully unreinforced slab, or an 8-inch with a little bit of steel fiber reinforcement, or some limited conventional reinforcement. You probably don't want to put more than 15,000 pounds on that if the subbase is decent. With a PrimX slab system of 4-inch and the subbase being also qualified and fairly decent, you can already put more than 15,000. You have to look at your base plate size and other considerations, of course. But that's not all. That's not all. That PrimX shrinkage-suppressed slab system is also going to allow you to lower drastically the amount of generated CO2. And I think if you're looking between 8 and 4-inch, it's closer to 3 million pounds of CO2 that you have saved for 500,000 square foot. It is enormous, in other words. And it's not only better because of the CO2 footprint reduction, but also because if you're a worker, you don't have to socket this. So you're not exposed to all the silica dust that is generated when socketing. which is really a real mess, and we shouldn't ever use that ever again, but people still do, unfortunately. Then, of course, building a flat slab that stays flat, that's essential. Some people are going to require very high flatness and levelness requirement. Indeed, they specify that they completely overlook the fact that that initial performance will not be there for long. Okay, so having a system that actually abides by a spec for a very long amount of time, or for its whole life cycle, is really another benefit here. Okay, so I'm going to show other pictures. You know, owner and tenant equipment damage. It doesn't matter if the tenant or if it's a tenant operated building or an owner. There are benefits for everyone. If you're a developer, now when your tenant leaves in 10 years, the retention value of that building is significantly higher. And I can tell you, in 10 years, a lot of folks are going to want seamless slabs that are much more hygienic, maintenance-free, and operate without completely ruining the forklifts that they have. And the smaller the wheels, by the way, if you use small robots with small wheels, the more dramatic the impact of these some joints that you really don't want to have in your workplace. And yet we still see them. But okay, we've discussed all these benefits. Without putting a number on it, I know I alluded to the use of too many wheels. But if we look at a 500,000 square foot warehouse, excuse me, that would be a big house. But anyway, the 500,000 square foot warehouse, the maintenance impact, and if you look at conservative figures, can be screened around very conservatively at about just short of $1 million US. These are US dollars, by the way. And people don't even realize that. And this is very conservative. So you are unlikely to be below that. That is the reality. Between joint sealant, joint damage from equipment repair, and tire replacement, a huge component of this. And then you have to think about safety, handling speeds, employee morale. I have a very large retail client who told me the first thing we show to the guys that are going to drive the 450 is how nice of the working surface they have. So now you have an advantage of the local labor market. Well, there's been times here in Calgary where everybody would want to hire their neighbor's warehouse operator. Okay, so in a situation like that, it's much neater to operate on a monolithic, beautiful, continuous, and seamless surface than to operate on a surface that's been depleted, destroyed, repaired, curled, moves, and whatnot. And those defects, they happen every time you have a control zone joint indeed. So we're proposing to reduce that. If you look at a 500,000 square foot warehouse, you'll have 15 miles of joints in there. And by using what we do, probably 0.5 mile. And then again, these are just construction joints. And in an ambient setup, that 0.5 mile of construction joints, they barely open, or they just activate. Indeed, there is not the shrinkage component to open those joints. And you gotta imagine that your panels in an ambient setup, they're gonna be 30, 40 to 50,000 square foot whenever you're stopping to pour in the day. And so the distance between two day joints can be 300 foot, 300 feet, essentially, in one direction, and who knows, maybe 150 in the other one. But in the end, you can easily design and build totally seamless panels without even a day joint or a construction joint. And these panels could be 40 to 50,000 square foot each, depending on concrete supply, how much people you can have at the same time finishing the slab and all that. Okay, so very great benefits. And that 950,000 USD figure over 5 years is a very conservative figure indeed. So flatter, we discussed that, but another thing is, if you look at how people measure flatness and levelness, if it's a slab full of sawn joints, they measure only a small portion of it because they're not allowed to measure in the vicinity of the joints. So, you know, even that report doesn't accurately represent There is a dog in the office. I don't know where that comes from. I'm going to close the door. Apologize for that. If you're using a seamless slab, now really, if you're measuring the flatness and the levelness, well, you're going to measure 100% of that surface. Okay, so whatever report you're going to get is not only going to more accurately reflect the actual situation, but that report is going to be sustainable and durable in whatever it's telling you. Okay, so flatter long term, we discussed that. So of course, flatter is better if you have to reach higher. Also, interestingly, PrimX, the technology as used by Alphacon, indeed has a partnership with Hilti. So Hilti makes anchors and has developed a program, an R&D program with PrimX, so that we can develop any mechanical anchor you need, even if the slab is thinner, without burdening the pull-out, the pull-out force necessary to destroy the anchor. So it is already assessed, and Hilti has a product that can work with the PrimX slabs, and it's been tested, but considering lower anchoring depth. Okay, so that's very important, because if you have a 9-inch slab and somebody wants to come with a 5-inch anchor, and that slab should only be 4-inch if it is shrinkage suppressed and seamless, you don't want another trade on that job telling you can't use that thickness because the anchor is going to fail. No, just call Hilti. They have a product for this. It performs very well. So that is also the message, is that sometimes you have to work cross trade in a project, and I do that a lot. That's something I enjoy a lot indeed, is to see what is the impact of what we do at Alphacon on other trades, and in this case, indeed, clearly racking. Okay, so then of course what we provide, because we are somehow confident in our outcomes as provided, we also provide a 5-year warranty. It is the most comprehensive warranty you will ever see. Okay, because nobody's going to guarantee for 5 years, certainly not for curling. Guaranteeing against cracking, indeed, that means that we will monitor and repair the cracks, but our objective is indeed to lower the probability of cracking to the lowest achievable and possible. And I believe that David, our champion and sponsor today, visited one of my freezers in Calgary with panels that were 20,000 square foot, and he can now tell you what it is. The lowest probability of cracking. In that case, it's almost other than one very tiny little crack somewhere that's completely limited and controlled. There is 0 cracks in there. Okay, so that closes the presentation. Please ask us about visiting references if you want to learn more about this. There are references in Alberta, Ontario, and BC, including in Seismic service as exposed and shared by Kevin. These are some of the references using this technology. Some of them are Canadian, indeed. I suppose, David, that we have a little bit of time to address some questions by the audience. And I would like to first thank everybody again for your precious time. I hope this presentation was valuable and a good training to you. We welcome feedback. If you need to personally tell us about feedback, I listen to what you found about the presentation or comments you would have. And if you would like to ask questions, now is the time, and you can always, of course, email me or contact Kevin with more questions. Do we have a question?
Yeah, I'll just jump in. Thanks very much, Francois and Kevin. That was actually fascinating, really informative. Lots of technical information there. I think you've probably overwhelmed us quite a bit there, but it's a good thing it's recorded, and it will be on the website, the Canadian Prairies Group of Chartered Engineers website, in a couple of days. But yeah, let's open up to questions. So I'll hand over back to Hugh. I think he is monitoring everybody's audio, and open up to questions.
Yes, I hope everybody can unmute themselves if they want to raise a question. So I think you just have to click on your mute and it'll unmute it, and then hopefully you can ask a question.
Can I start? I'm sure there's lots of technical questions, but there was one that intrigued me. Can you hear me?
Yes, we can hear you,
okay.
Alan.
Yes, it is. I was wondering, you raised earlier in the presentation, in your presentation, Kevin, about using the Concrete Society's methodology, TR64, instead of the Canadian standard. And I'm wondering, did you need to get a waiver in order to do that? And if so, I wonder what the insurance implications would be for the owner of the buildings involved. Would they be happy, or were they happy with you using a standard that's, I wouldn't say not recognized, but I wonder how you dealt with that issue of
Sure.
using a standard that's not Canadian, put it that way.
So the CSA 823.3 specifically precludes slabs on grade from being considered a part of the structure. So
Right.
for the Burnaby structure, it's not an issue. The CSA 823.3 also allows the engineer to use other methods that can be demonstrated to be valid, as it were. And there is no guidance that I know of in CSA 823.3 for the use of steel fibers in bending. You can use, I think there's a clause that allows you to do a little bit of shear work, but there's a great dichotomy between, or a great separation, I should say, between what occurs in Europe and what's occurring in North America, both Canada and the United States. Now, the Canadian code is since I work with both of them, I'll tell you the Canadian code is well in advance materials-wise of where the American Concrete Institute code is. I sit on the material subcommittee of the ACI building code, and so I don't I don't speak of this as a casual observer. And I know Doug Hooton very well at University of Toronto, and he's the current CSA 823.1, 823.2 chair, and so I'm sure he would agree with me. But the interesting thing is that if we because we haven't reduced things to practice, there's no we did have to demonstrate, of course, to the building officials both in Calgary and in British Columbia that the methodology was sound, which we did, and throughout the world, and this is what makes civil engineering somewhat interesting. I was getting a kick out of it. My training is partially in chemical engineering, as is Francois's, and between the difference between civil and chemical engineering can be, and mechanical engineering for that matter, can be quite interesting, right? We use somebody uses Darcy's friction factor. Someone uses Fanning's friction factor. They're the similar in concept, but I think as a general rule, although Canada is far superior in this way to the United States, the codes are lagging, and they're lagging significantly. And one of the reasons in structural design that they're lagging significantly is because we have been so happy. The Whitney stress block allows us to design structures and make assumptions that give us safe structures.
Right.
And so that's perfect, but it's not the only way to skin a cat. And in terms of suspended slabs, which we're not talking about here, you would look at it one way, but in terms of soil supported slabs, it's a little bit simpler.
Yeah, well, maybe you'll indulge me with another question, and that is, could you distinguish between, when you're talking about the distribution of the fibers, between uniformly and randomly distributed fibers? Are the fibers what are they? Are they randomly distributed? And
I'll
if so-
take this one. That's a very good question, and I will take it. So with this, you know, this is a statistical question that you're asking,
Mhm.
essentially. Yeah. So randomly, that's very true, because every fiber can take any orientation as statistically provided, so within the concrete body. And that means that these fibers take an infinite amount of orientation.
Mhm.
And that is precisely very different from discrete steel reinforcement.
Right.
And Kevin can elaborate a little bit more, but here the homogeneous distribution is essential, because we're creating a composite for which we want the properties to be constant, regardless where we look at on that concrete body. So homogeneity is very true, and that is at the heart of our operations. We discussed the install briefly, but indeed that is at the heart of it. And then the fact that the fibers can adopt any orientation possible, yes, absolutely, that is true too.
Yeah, and that's a good answer. The simple question is that they are uniformly distributed, so that there's no area, no particular portion of the concrete has more fiber than another, but that they are random in their orientation.
So in practicality, how do you get an homogeneous distribution? Well,
Right.
first of all, there are certain things you don't want to do. Using conveyor belts with nesting and balling of the steel fibers, which is essentially what is done everywhere else.
Yeah.
And another aspect of things is that you don't want these fibers to already ball as they are conveyed or brought into concrete, because we don't use conveyors. We use fibers that come in a known mass into a rotating squirrel cage. So the fibers are dumped into a rotating squirrel cage, and then they fall due to gravity into a venturi system. That venturi system then blows the fibers at about 100 kilometers per hour in the back of the truck. But at that time, the fibers are separated from one another. So imagine this is the best way to start homogeneity, because as I said earlier, the concrete truck is the worst mixer invented by mankind today. But it does indeed put matters in movement, so that you are incrementally going to add fibers to that concrete mix at every element of volume of that concrete. That you know you will do very well. There's a time factor to this. I mean, if you want to put 40 kilo per cubic meter in a 10 cubic meter concrete truck, it's going to take you 7 or 8 minutes, okay? And then you have to also add the other additives. So there is time, expert labor, dedicated and properly designed machinery. But I note that these machines were designed by my father in 1982, and they've been operating for 40 years, and they've been probably used to make to date, and we're not certain exactly, but we think about 3 billion square foot.
Well, thanks very much. I need to make way for other people to ask questions, but thanks for the replies.
Thank
I
you.
think Nigel had a question. Do you want to go ahead, Nigel?
Yeah, thanks, Hugh. So I thought that was great, Francois and Kevin. I really appreciate the talk. Thank you very much. I had a couple of questions. The first one was that in the introduction, Francois was saying that his father looked at Roman concrete, and then this is built from Roman concrete, but I don't know that the Romans had steel fibers. That's one issue. The second one would be that your answer to Alan Murray just now, and that you said that the fibers are randomly oriented. I would agree that in the center, the core of your slab, that would happen. But as you get to the surface, they must become more oriented randomly within a plane, because they don't stick out of the surface. So there must be a shift in distribution as you get to the edges of your slabs. Is that correct?
Yes, and that's due to
Certainly at the top.
Sorry, Kevin, go ahead. You take that one.
Well, yeah, certainly at the top, they are going to be oriented. And no, the Romans had a number of things that they used for reinforcement, including horsehair, but not steel. They probably would have been a little bit even more successful than they already were had they had steel, probably made of weighted weapons first.
And back to what Nigel you were asking, the Roman concrete is notorious for being very durable, to not have cracks and not have shrinkage. And in that sense, that is what was interesting. And what was more interesting is to not do something that was already available, because shrinkage comp additives, they do exist since the mid-50s, as I mentioned, and Kevin mentioned that further into the 60s. So the idea here was to really have a total process, including reinforcement, shrinkage suppression, the maintaining a small expansion at long times. And it seems that the Romans were very good at ensuring there was no shrinkage for very, very long times. And so in that way, it was very purposeful to investigate them starting in the early 2000s for my father.
Yeah, so my understanding of Roman cements or concretes was they were more pozzolanic based than Portland. Well, they didn't have Portland cement, but they were certainly pozzolanic based. The main question I had was that you started to discuss the actual construction procedures. So it takes 7 or 8 minutes to blow the mixes into the concrete truck, and then you've got to place that on site. So what's the setting time? How much, are you rushing, or do you have a fairly long setting time so that you can actually place this and smooth it reasonably well?
Well, every setting time is different. Okay, there are a lot of factors affecting setting time, but you are correct that you don't want that improved concrete to stay in your truck for 2 hours. That's probably a very bad move.
Yeah, right.
But you don't have to rush it in within 7 minutes.
Okay.
Now, with this, it is true that the hydration of cementitious materials is an activated reaction. So there are a lot of things that are going to change the way concrete set and the kinetics essentially of hydration of the cementitious material. So in this case, for example, concrete temperature is a factor. Okay, weather can be a factor. The nature of your cement can be a factor. But I think I framed a little bit my answer by saying you won't have 2 hours, but it's not going to be 7 minutes. Okay. Now, if you're a good contractor and when you finish concrete and you understand the concrete quality, you can look at concrete and know what is going on with that concrete and have an idea. The idea here is that with the data collection, and what we do is that we reproduce known outcomes at every job site, but also on the same job site every day. Okay. And that's why there are procedures and a quality process. And perhaps, Kevin, you want to add on to what I said to answer to Nigel?
Yeah, the concrete will set normally, so you have the normal amount of time, and based on the binder compositions, you can use the same types of retarders. I think the biggest difference is if we look at Roman concrete in terms of its pozzolanic activity, we rely today on mostly on Portland cement, although I've done lots of projects where there's very little or no, 50 kilos per cubic meter or less of Portland cement, the rest of it being pozzolan. But the biggest difference is the development of calcium aluminate sulfates, calcium aluminate silicates, as opposed to just calcium silicates. And I think that's where the Roman concrete concept comes in. There's a great group of people called it's Romacon, I think, for Roman construction, and they go around and they've taken a number of cores from places like the Port of Trajan, like some of the or many of the seawater facilities, and you can see the similar materials that are present in Roman concrete that are present here in the PrimX.
Good, thank you.
Thank you for the question, Nigel. Any other question?
Oh, Francois, it's Hugh. I did have one question, and that is, you were mentioning you keep the concrete surface wet for up to 14 days. And
correct.
That's what I had understood. Maybe I misunderstood it, but if it is required, how do you ensure that happens?
How do you ensure that happens? Well, procedures. Okay, first of all, a wet cure is a wet cure. A wet cure, when it is implemented, the first objective is to saturate that concrete surface, because if there is liquid water, well, intuitively we understand that concrete is unable to lose its own water, and there is a lot of free water in concrete. So in fact, the reactions we use, without entering into the details, these reactions consume water. So they are not going to only consume water within the concrete body, and that free water is certainly available because there is still water in excess in those concrete bodies, but it is consumed by the expansion reaction. There is one location where it might be less available and where the concrete might lose water faster, is at the surface. So that's why that surface is then maintained wet, and that is with liquid water interacting with the concrete surface for 14 days. And in the beginning, there is a little bit of water consumption, so you have to maintain your wet cure. And that wet cure should be checked every day with water added on. Now, of course, there are different products that you can use, but the objective is always the same in terms of a good wet cure. It is water in quantity constantly during the wet cure period.
Okay, thank you, Francois.
Francois, can I just add in that on a project just recently completed, the one that Francois was mentioning, the wet cure, what the contractor did was they put down some mats, and I apologize, I can't remember what that exact product was, which retained the water. But basically for the first 14 days, it meant that somebody had to be there at least daily, checking to make sure that the moisture content was there, and if not, spray it down with water. So you're using actually quite a lot of water to do that, to maintain that water on the surface. But there was, as I said earlier, there was a mat laid which allowed the water to stay there, and it never dried. And it was only after 14 days that those mats were taken off and the surface was allowed to dry.
Thank you, David. I can add that towards the beginning of the wet cure, you might have to bring add-on water. That is way less the case after, for example, the second week of the wet cure. You barely have to add on, provided you have a high quality wet cure material. And that's often a one-time use wet cure that could be a double poly or a poly with an absorbent material below. Essentially, what you want to control is the interaction with that water with the ambience, okay? Because the drier your air, the more that water will have an affinity to go from liquid to water vapor, and that's where you have to add on. Then, like I said earlier, the concrete surface will absorb a little bit of that water as well. But yes, by having controlled procedures and ensuring that this is happening well, you maintain a good wet cure for 14 days. There is nothing difficult with that. It's a little bit of hosing and labor indeed, but it's well worth doing it, considering the outcomes that you provide once you remove the blankets.
Yeah, one consideration is that you have to have access to a reliable source of water as well. So if you're out in the middle of nowhere where you don't have a water supply, then it could be an issue.
Correct.
Can I ask, the bulk of your presentation, of course, was about warehousing and warehouse floors, but I think you hinted that you could also use the slabs in a multi-story building, right?
Yes, so that's not done in Canada yet.
Yeah,
but it is in Europe extensively so. And,
I'm wondering how would they do the tie-ins to concrete columns?
Okay, very good question. The only rebar that is present in the elevated suspended flooring systems that make up for every floor of that structure, it's the anti-collapse bars that you will find at columns on centers. So essentially, these structures are designed for column suppression, which some people call terrorism. But indeed, you have to be able to suppress a column while maintaining the integrity of the structure, and that's certainly not that structure experiencing progressive collapse. So you have to keep your bars at columns on center, but these bars are no longer present anywhere else. The slabs are then provided sometimes with a higher dosage of steel fibers, even 50 kilo per cubic meter, and the slabs are designed in elastic service. I know that this is a technology and an approach to the structure that does exist for years and years, and that the first suspended slabs with steel fiber enforced concrete only at extremely high dosage and in structural service were built in the UK around 1992. There are hundreds of references like that, and indeed the next step was to then build these structures with the floor slabs are not only suspended on columns, but they're also elevated. And Kevin, you might want to add on to that. I think you had a comment about USA and Canada design practices. In Europe, we're doing that already, but maybe you want to add on to that, Kevin. And I don't know if Kevin was able to hear me, but there is an ACI document, ACI 544, which treats essentially and exclusively elevated steel fiber enforced only slab bodies. And so you're looking at ground zero when it's a warehouse built on piles, but you're also looking at every floor above, which then is often a residential condo tower. Now, sorry, Kevin, your turn if you wanted to add something.
Yeah, it's the building codes that are giving us the problem, not the mechanics of things. And so we need to look at, you know, the codes are necessary for life safety. And as I said, I have just completed a term as the American Concrete Institute's chair on their board level committee on responsibility. And so, you know, I do a lot of failure evaluation. So I don't take it lightly, but you know, we have a series of assumptions that we have put together for these slabs and for design of reinforced concrete structures that are not always following the state of the art. But where you have highly concentrated loads, particularly where you would have column to slab connections, you'll need discrete reinforcement. It's the same way if you build high-rise construction, you'll frequently see people that will puddle a high-strength concrete around the area or install drop panels, that sort of thing, to increase the capacity of the slab due to punching or what have you, only where it's really required around the columns. And you can think of the steel as the same thing, but you can use, particularly in terms of concrete slabs that are combined with pre-stressing, you can use a little bit less pre-stressing and considerably less reinforcement.
Another question, perhaps? I don't hear Hugh coming with possibly another question. No, let me see that the chat is actually sending something. Okay, thank you, Alan, for your message. Any other question? No. Well, I would like to then first and foremost thank my co-presenter, Kevin, for not only his contribution to the presentation, but also his passion. And for my pleasure to work with you, Kevin, on the projects that we have completed together. I hope to do much more. So thank you, Kevin.
That's mutual, and I love talking about engineering. I'll do it, and it's either talk to you guys who are interested, or talk to my wife and children who think that concrete is very boring.
And thank you also, Hugh and David here today. You have my email on this slide, so if you want to privately talk to me, or talk to Kevin. I think Kevin emailed his contact here in the chat. We are available, personable people, real people. We like a challenge. We like a real project. Think about this when you are designing, because you have a lot of say in your career, so as to how things get built. And I think in the disciplines of engineering, and we have a lot of engineers, and Kevin and I are, of course, engineers primarily. I always say that, and Kevin said it before, the difference between a fool and an engineer, but I would say this: if you are looking at the physical sense and looking at with curiosity, with the mathematical tools combined with experience, with observations and with curiosity, that's real engineering, real noble engineering. By always following the same protocol without questioning it, using numerical simulations only without understanding totally the physical sense of things, then engineers tend to behave more like accountants. And that might be fine, but I've always tried to not do that. And I believe Kevin would agree with me to some extent in that statement. Again, thank you, Kevin, for your role today. And thank you, everybody. We will adjourn unless, Kevin, you want to say a word. Probably you do.
If nobody else has got a question, then maybe I can just, on behalf of the Calgary Prairie's group of chartered engineers, thank you, Francois and Kevin, very much for a very interesting talk this evening. And then thank you, everybody else who dialed in this evening. It is good to see. I think we had more than 20 people this evening, so really appreciate everybody dialing in. And with that, I'm going to stop the recording. Thank you, everybody.
Did you want to have a last word, Kevin, before we adjourn?
No, other than to say thank you very much.
Okay, thank you, everybody.
Thank
Talk to
you.
you guys soon.